January 28, 1986, 11:30 a.m., Kennedy Space Center. The Space Shuttle Challenger is awaiting its launch in less than 8 minutes. And in less than 10 minutes, the Challenger will explode in the skies over Florida in a catastrophic end to its 10th mission. After the Apollo project and humanity's arrival on the moon, space shuttles were NASA's response to the new objectives of the American space program, to launch missions into space more regularly and more cheaply. Space shuttles were a partially reusable technology, which reduced the cost and time of launch between missions. NASA's dream was eventually to launch more than 48 space missions per year using space shuttles, and to sell cargo space as a way to fund its own scientific projects, reducing reliance on government resources. The Challenger disaster represents the end of that dream. Launching a space shuttle like Challenger is an exercise in engineering and integration. A space shuttle has 4 components that together can launch one of the parts into space, the orbiter, or the orbital spacecraft. The star of the show is the orbiter, designed with the capability to operate both within and outside the atmosphere. This means that the spacecraft can return from space and land on a runway like an airplane. Despite this extraordinary capability, the shuttle still needed help to reach space. And this is where the other 3 components of the space shuttle launch come in. A gigantic liquid propellant fuel tank, called the external tank. This orange tank carries hydrogen and oxygen for the space shuttle to use during liftoff. On each side of the external tank are 2 solid rocket boosters, referred to by the acronym SRB. These rockets carry a solid propellant in the form of hydrogen, which generates intense propulsion when burned. The SRBs will burn their solid fuel during the first 2 minutes of the flight to provide the final boost that the Challenger needs to reach space. And after burning, the boosters separate from the shuttle and fall with the aid of parachutes into the ocean, where they are recovered and prepared to be reused in a future launch.
Hey, Pedro here. This video you are watching was originally in Portuguese, my native language. This is the attempt of our team to translate it to English, and I sincerely hope you enjoy it. Your feedback is extremely important to us. Now, back to the video.
January 28, 1986, 11 hours, 37 minutes, and 54 seconds. Kennedy Space Center. After 6 days of delay and a cold night, the Space Shuttle Challenger was finally launched. The shuttle's main engines ignite using fuel from the external tank. 6 seconds later, the boosters ignite and the Challenger begins to lift off. 36 seconds after liftoff, the shuttle reaches 3,000 meters in altitude and starts to experience the effects of strong winds. The Challenger's computers initiate automatic maneuvers to compensate for the wind effects. At 58 seconds, a plume of smoke becomes visible on the right side booster. The shape of the plume changes over the next few seconds, indicating that some of the fuel is leaking. At 72 seconds, pilot Michael Smith speaks into the microphone. A little over a second later, an explosion separates the spacecraft from the external tank and the boosters. The launch of the Challenger suffered a catastrophic failure. Numerous family members and friends of the 7 Challenger crew members were watching and were in shock. To make matters worse, the Challenger was a historic flight, and one of the crew members, Krista McAuliffe, was chosen to be the first civilian in space through the Teacher in Space program. The entire American nation was watching this launch, which has now become a disaster. February 3rd, 1986, Marshall Space Flight Center. After the Challenger disaster, NASA needed to answer 2 questions. What caused the accident, and how can we ensure it never happens again? But the only response NASA gave in the following days was, "We are investigating the issue." Investigations that never became public due to NASA's actions. Internally, the atmosphere was one of panic, and no one at NASA wanted to commit to an unfortunate public statement. President Ronald Reagan had to postpone the traditional State of the Union address because of the Challenger disaster. On February 3rd, the American president convened an independent commission to investigate what happened. The commission was chaired by the 55th Secretary of State, William Rogers, with Neil Armstrong, Deputy Director of the Advanced Aeronautics Research Center of the APA, as Vice Chairman of the commission. And of course, Neil Armstrong was also the first person to set foot on the moon. The testimonies about the Challenger disaster for the Presidential Commission, or the Rogers Commission as it became known, began on February 6, 1986. The first days were mainly about explaining the design of the space shuttle to the commission. The witnesses of the commission were mainly members of NASA and the companies contracted to develop and produce the equipment used in the space shuttles. February 9th, 1986, Washington, D.C. Amid the early days of the Rogers Commission's work, two internal NASA memos were leaked to the press. The memos were written by Richard C. Cook, a budget analyst, and both had the same topic regarding the boosters, the field joint O-rings. For ease of assembly, the boosters were made in sections that had to be joined near the launch pad. Transporting pieces was easier than transporting the entire booster already assembled. The connection between the two parts is a joint called a field joint, precisely because it is made in the field outside of a factory. A disassembled booster is convenient, but it also presents problems. Field joints are a structural weakness. The joints, in fact, open slightly during the most extreme moments, especially from the start of ignition at 0.6 seconds. It is necessary to reinforce the joints to prevent high-pressure fuel leakage. The O-rings are part of the protection against gas leakage. In the case of the Challenger, they were made of high-performance rubber and were designed to seal the gap caused by the field joint. And Cook's two memos raised concerns about the O-rings. The first memo dated 6 months before the Challenger disaster, and Cook identified the O-rings as a budgetary threat, indicating that they were not operating as desired by NASA and that it might be necessary to spend money on a redesign of the O-rings or the field joint, which had already undergone a couple of minor redesigns, but it was still not sufficient. The second memo was issued a few days after the disaster, in which Cook informed other NASA members that the team of engineers was convinced that the Challenger's problem was with the boosters. February 11, 1986, Washington, D.C. February 11th is the day when the Challenger disaster stopped being an accident and became a catastrophe caused by NASA's negligence. On February 11th, the Commission was interviewing NASA's official responsible for the boosters, Lawrence Molloy. The first noteworthy event was the so-called Feynman experiment. Influenced by Cook's memos, Richard Feynman focused his attention on the O-rings. Feynman asked Molloy if there was a temperature limit for the safe operation of the O-rings. Molloy responded that there were data indicating that the material of the rings worked between -34 degrees Celsius and 260 degrees Celsius, which is not exactly true. Yes, there were some uses of the rubber in the O-rings that were suitable at those temperatures. There were no tests ensuring the proper operation of the O-rings on the boosters below 4 degrees Celsius, with the lowest launch temperature of a space shuttle before the Challenger being 12 degrees Celsius. Feynman demonstrated the problem with Molloy's response by placing an O-ring in a glass of cold water and showing that the material's elasticity was compromised by the low temperatures. During the launch of the Challenger, the temperatures were 2 degrees Celsius, below the tested limit for the proper operation of the O-rings. The night before the launch was so cold that it created large amounts of ice. Molloy was repeatedly questioned by the rest of the Commission about concerns with the temperature and the sealing rings before the flight, and all his responses indicated that no serious concerns had been raised about the cold. All responses indicated that the Challenger was an unpredictable accident and that nothing could have saved the lives of those 7 astronauts. And one person in that room knew it was a lie. Twice during Molloy's testimony, one of the chief engineers from the company responsible for the O-rings raised his hand to get attention, and he was ignored by Molloy both times. The engineer calling for attention was Allan McDonald, and for more than 6 months he had been reporting failures with the O-rings in the booster design to NASA. McDonald knew that Molloy was as informed as he was about the recurring problems with the O-rings, and that these problems were intensified by low temperatures. To Allan McDonald, it was very clear. Molloy was lying and covering up the failures in NASA's decision-making process, and Allan had decided to tell the truth to the commission chaired by William Rogers. After a pause, instead of raising his hand at the back of the room, Allan McDonald simply got up from his seat and walked to the middle of the room, interrupting Lawrence Molloy's testimony. Allan McDonald's account changed the course of the investigation and made it clear that the Challenger was not an accident, but a disaster due to a failure in decision-making by NASA and the company responsible for the boosters. And this is the story that Allan McDonald personally experienced and shared with the Commission. There were recurring problems with the sealing rings, some recorded in tests almost 10 years before the Challenger disaster. Each field joint connecting the parts of the boosters has 2 O-rings, called the primary and secondary rings. Originally, this system was considered a critical 1R system. Having criticality 1 meant that a failure in the O-rings would lead to a catastrophic mission failure. But the letter R stands for redundancy. If the primary O-ring failed, the secondary ring should be able to prevent fuel leakage through the field joint. The second flight of a space shuttle in 1981 showed erosion of the primary O-rings. Tests and subsequent flights continue to find recurring failures in the sealing of the first ring of each joint. The failures were so common that the rings were reclassified to a critical 1 system in 1982, without the R for redundancy. The failure of the first ring due to erosion was so common that it began to be treated as expected. And this represents a trend at NASA during the 4 years between this reclassification and the launch of the Challenger. In 1984, erosion was detected in the secondary ring, indicating a complete sealing failure by the primary ring. Moreover, during the first launch of the Space Shuttle Discovery, soot was found between the primary and secondary rings, indicating a new type of failure, much more serious than erosion. During the Space Shuttle launch, specifically at 0.6 seconds, the forces on the field joints were so intense that they caused them to bend slightly. The presence of soot between the sealing rings indicated that the primary ring had become unseated during launch, losing its function of preventing fuel leakage and leaving all the work to the secondary ring. The unseating occurred when the field joint bent and compressed the sealing ring, and due to a lack of elasticity, the ring failed to return to the correct position. The lack of elasticity was worsened by low temperatures, which made this failure more likely on cold days, like the day the Challenger was launched. And there was no guarantee that the secondary ring could maintain the seal in such a failure. The erosion problem was unpleasant, but by the time an O-ring eroded enough to be a problem, the shuttle was already halfway to space and the ring had already fulfilled its function. However, the problem of an O-ring becoming unseated during launch was much more serious, a sign that a possible catastrophic failure was on the horizon. So it was necessary to investigate the issue more thoroughly, or at least that was the opinion of the engineers responsible for the rings and boosters like Allan McDonald. NASA's administration had other things on their mind. The idea of investigating the problems with the O-rings more thoroughly was not taken as seriously as it should have been. NASA was under extreme pressure to conduct space shuttle launches more and more frequently, and eventually sustain itself by selling cargo transport to space. The idea of halting or delaying flights due to O-ring failures was a serious budgetary threat. On the other hand, the company responsible for the O-rings, Morton Thiokol, had far more people focused on securing contracts with NASA than investigating the failures of the O-rings the company produced. Allan McDonald worked at Morton Thiokol. Even the day after the Challenger disaster, the company was more focused on securing its next contract than investigating the cause of the disaster. What happened in the years before the disaster was a slow but consistent expansion of the comfort zone regarding the launch risks by NASA and Morton Thiokol. With each launch and additional tests, the problems with the sealing rings became increasingly serious. Each time the problems were reported, the risks were analyzed and someone decided that the risks were acceptable. Sometimes the risks were tolerated for good reasons, but sometimes not so much. The slow but consistent increase in the comfort zone reached its peak on the night of January 27, 1986. The night of the 27th was not the first safety meeting for the launch of the Challenger. The launch of the mission had already been delayed for 6 consecutive days. The launch window was already nearing the acceptable limit for some of the experiments on board. Furthermore, if the mission were delayed by another day, it would also not be possible for teacher Krista McAuliffe to conduct the space lesson. NASA was already under pressure for more regular launches in 1986, and these particular factors further increased that pressure for the 10th launch of the Challenger. The night of January 27 was not helping. The night was extremely cold, much colder than expected for winter in Florida, and the temperature forecasts for the next day were near 0 degrees, even at the launch time, below what any previous flight or any test of the O-rings had ever experienced. And it was precisely this concern that engineers Allan McDonald and Rogers Bajoli raised to Lawrence Malloy at the flight safety meeting on the 27th. The presentation was emphatic. It was not possible to ensure the proper functioning of the safety rings at temperatures near freezing. The flight should be postponed until the temperatures rise again. In any normal safety meeting, that would have been the end of the story. The flight would have been postponed again. And very likely this video would not exist, but the engineers' concerns were countered by Malloy with mockery and aggression. When do you want me to launch? In April? Malloy and NASA leadership stated that the engineers from Thiokol were wrong and that they had no evidence to support the claim that flying was dangerous. Even so, NASA would not launch Challenger without the launch confirmation from Thiokol. And this is where the comfort zone expands beyond the tolerable and turns safety criteria upside down. Until then, the launch criterion was as follows. If it is possible to prove that launching the space shuttle is safe, the launch happens. If not, the launch does not happen. In the middle of the meeting, the engineers from Thiokol were challenged to prove that the launch was not safe. While they reassessed their analyses, the management of Thiokol was talking alone, away from the engineers. And after 30 minutes of a private meeting at Thiokol, Joe Kilminster, one of the company's leaders, gave the affirmative recommendation for the Challenger flight, which went against the recommendation of the company's own engineers, unless they could prove that flying was not safe, which they couldn't do. The opinion that the Challenger should not fly stemmed from the fact that it was impossible to prove it was safe to fly at those temperatures. Now, the lack of evidence and clear data was used in favor of the launch for the first time in history, a reversal of roles. And for the first time in history, NASA asked Thiokol to confirm the launch recommendation with a signed document. A clear indication that even NASA was concerned about the flight situation. Allan McDonald refused to sign the document, and Joe Kilminster signed in his place. Despite the cold, despite the concerns, the launch took place. And not only did it happen, but almost no one in the control center was informed of Allan McDonald's concerns. The astronauts aboard the spacecraft were not even aware of the recurring problems with the O-rings, as 4 of them had flown on past missions where the O-rings had shown some level of failure. NASA's secrecy about the O-rings indicates that they knew they were operating at the edge of what was acceptable. January 28, 1986, at precisely 11:38 a.m. At 11:38 on January 28, the Challenger was launched for the 10th and final time. 0.6 seconds after launch, a gas leak occurred from the field joints. This indicated a sealing failure, the exact problem that most concerned the engineers at Thiokol at the time when they expected something like this to happen. Due to this failure, the launch of the Challenger was in a precarious position, and the solid fuel could freely leak from the field joint. 2 seconds after launch, the leak stopped. It appeared that some piece of solid fuel resealed the joint, performing the function of the O-rings that had already failed at that point. The accidental seal kept the booster relatively stable for the next 56 seconds. As the space shuttle approached its point of maximum aerodynamic forces, the joint began to be affected again. 58 seconds after launch, a plume indicated a booster leak. The plume grew, indicating the presence of fire. 73 seconds after launch, the booster exploded, separating the space shuttle from the external tank and the 2 boosters, ending Challenger's 10th mission in a failure with the loss of the crew. A failure in the O-rings led to the tragic end, and a failure in the separation between administrative and engineering decisions led to the decision to launch the mission, even with the safety risks raised by the engineers. In the statements of those interviewed by the Rogers Commission and in the flight safety meetings, there was an appreciation for the idea that the safety of the astronauts should be prioritized. A manned mission should not be launched unless the chance of success is almost 100%. But as Feynman points out in Appendix F of the Rogers Commission report, this emphasis on safety was rhetorical. There was no clear engineering criterion defining what it means for the mission to have almost a 100% chance of success. It was the flexibility of a vague criterion that allowed NASA to continuously expand the comfort zone to include more and more signs that the O-rings were not a safe technology. The concerns of the mission engineers were ignored or minimized by administrative decisions, primarily focused on ensuring NASA's image and the financial resources of space exploration. The same logic applies to all companies contracted by NASA. The appearance of doing a good job to secure the next contract was more important than correcting flaws in the project. After all, correcting a failure means admitting that a failure exists and reducing your chances of securing a new contract. Every time a problem was pointed out, it was possible to find a new justification to move forward and still consider the mission as almost certain. And this worked for dozens of missions, which slowly created a sense that nothing could ever go wrong. The precision engineering that led to dozens of successes was replaced by a mythology that NASA could not fail. And this tragedy was not the result of an accident or a lack of technological capability on the part of NASA. In the rush to launch more and more missions, administrative and safety decisions became intertwined. On the night before the Challenger accident, engineers were humiliated for their technical opinions, and administrators made the decision to launch against the technical safety recommendations. Administrators knew they were wrong in doing this and tried to hide their choices after the accident. The great lesson from the Challenger disaster is that safety is synonymous with respect and trust in all the people involved in a process. Everyone involved in a major engineering project needs to have their voices respected and feel comfortable expressing their concerns. And it was ignoring the voice of Allan McDonald that led to a tragedy. NASA's administration did not believe that anything could go wrong until it did. And all the public confidence that NASA had after putting Neil Armstrong and Buzz Aldrin on the moon in 1969 was lost all at once, along with 7 lives and the entire future of continuous space exploration with space shuttles. May the story of the Challenger always serve as a reminder that when it comes to space, safety must come first, especially when human lives are at stake. Thank you very much and see you next time.